features of these colloidal rods, I will transform them into various shapes that you can see on top of that. Okay. So colloids are solid-like particles suspended in a liquid medium whose size is small enough such that they undergo Brownian motion due to thermal energy fluctuations. So, typical example of colloidal suspension is milk, ink, paint, and in very broad sense, colloid includes liquid crystals, polymers, emulsions, foam, so on and so forth. Now, if you take a dilute isotropic spherical colloid at low volume fraction, it shows fluid-like behavior, and if you increase its concentration, it shows crystalline-like order, where in between it shows fluid and crystal phase coexistence. Now, very nice thing about this colloidal system is that it has got well-defined shape and size of the building blocks. More importantly, you can tune its interparticle interaction, which makes it a very excellent model experimental system to test or to explore some of the fundamental problems in the condensed matter physics, such as kinetics of crystallization or nature of the gaseous state and problems like that. Another very important aspect of colloidal system is its length scale and time scale. So here is a colloidal crystal which can be thought as an analog of atomic crystal, but at much larger length scale, where you can so these are micron size, so you can visualize under optical microscopy and also track its dynamics and other related phenomenon, because the time scale associated with this is way slower than what you find in atomic systems. Now, another system of so you can have shape anisotropic colloids at low concentration. It shows isotropic phase, which the rods here are randomly oriented. So if you increase its concentration, Onsager in his seminal paper showed that if you increase its concentration, the rods more or less on an average align along a long axis, which is this phase is known as nematic phase. The direction of alignment is known as nematic director, and if you increase further, the layers of rods stack on top of each other and form the synaptic phase. So where you see a one-dimensional long-range quasi-positional order along this direction, and where within the layer rods are liquid-like. Now, one of the most important and very complex system made up of molecular rod-like particles is a cell membrane, which is essentially a lipid bilayer, and it has got a lot of embedded proteins, cholesterol, lipid rafts, ion channels, and like that. So as a soft matter physicist, we look for a model system, something consists of colloidal rod-like particle, such that we can do many things visually. We can visualize under microscopy, optical microscopy. So idea is to have, can I use some kind of colloidal rod and self-assemble something similar to lipid bilayer, which has got at least some of the properties mimicking that of lipid bilayer. So in this talk, I'm going to show you a system that which indeed we have a system which is known as colloidal membrane. So building block of colloidal membrane is actually a highly charged semi-flexible rod-shaped virus. Okay. So for all practical purposes, you can assume this to be a rigid rod because its persistent length is way longer than what you see this contour length. Okay. And also a highly charged, so we add salts into this to charge stabilize these colloids. So what we do is that we take dilute isotropic mixture of these virus rods and mix with polymer. Okay. So here you can invoke a hard sphere and a hard rod model. So that leads to a region surrounding this colloidal rod here, which is not accessible for this blue, the purple spheres which are depicting polymer coils here. Okay. So when these two rods come closer than the polymer diameter apart, then there is a overlap of the excluded volume. So that leads to free volume entropy, the extra free volume for these polymer coils, which in fact increases the system entropy because number of polymer coils are way larger than what we have for the rods. In another way, you can think of this as from the osmotic pressure point of view. When these two rods come closer, then the polymer particles get extruded from this region. So then there is an imbalance of the osmotic pressure. So that leads to condensation of these rods, right? So eventually, if you wait long enough, when you mix this, you will see a structure like this, which is schematic of a colloidal membrane. And in a real sample under the microscope, you will see. Yeah, okay. So you will see that. So this is a colloidal membrane. As you can see, it has got thermally fluctuating edge, fluid-like order, and it has got final bending rigidity, which are the properties quite similar to what you find in lipid bilayer. Okay, so one of the very nice thing about the depletion, so this is known as depletion force that I'm talking about. It's driven by entropy. Okay, so one of the nice thing about depletion force is the strength and range can be controlled experimentally, unlike some of the atomic interactions that we have in the system. So another very nice thing about this depleted polyethylene glycol, its osmotic pressure is dependent on temperature. So not only you can change the depletion force by the concentration of the polymer, you can also change dynamically by using this temperature. In fact, I'm going to show you, I use heavily on this nature of this polymer to do some nice stuff. So if you prepare a sample,
and the previous slide, what is the width and the diameter of that?
This one?
Yeah.
So it will be around 50 microns. So you can, the scale bar is 10 microns. So it can, if you allow it to grow, it can go to 100 microns. The nature of this virus, even though I assume that a hard rod.
Why this is making a circular cross section? Is some chamber is circular?
No. So it is because of surface tension also plus chirality.
Chirality.
Yeah, chirality and surface tension. That would line tension in this case. So yeah, so another very complex nature of this virus is that they intrinsically chiral. What I mean by that, two rods if you take, they prefer a finite tilt with respect to its neighbor. So then, here's the two forces acting. The depletion wants to make them align along they are parallel. Okay, they favor parallel alignment, whereas the chirality wants them to tilt. So there is a frustration in the system. So the system is resolved by expelling the twist to the edge of this membrane. So, and here's a fluorescence image of a membrane where few of the rods are again labeled. As you can see, the bulk of the membrane there appear dot, whereas the edge is completely, you can see the entire rod. Okay, so this you can study more quantitatively using an advanced polarization microscopy, which is known as LC pole scope, where this is a retardance image where the pixel brightness in this image directly relates to the local orientation of the rod. So that's why, and the light is incidenting perpendicular to this plane of the membrane. So that's why you don't get any birefringence signal from the bulk of the membrane, whereas the edge you will see a uniform bright ring that's capturing this rod thing because rods are tilting. And if you take a line cut here, then you will know how much the twist is getting penetrated to the membrane edge. So that's around half micron for this, and which is independent of size of the membrane. Okay. Yeah, so what I want you to remember from this slide is that rods at the bulk of the membrane at the edge are not same. They're oriented differently. In fact, yeah, a very uniform twist from here, from being straight to very smoothly it goes to lie on the plane of the membrane. So then I come to my thesis outline. So there are 4 work chapters. So in the first chapter, I'll talk about existence of a curvature instability in a 2D fluid circular membrane, which exists because which shapes the membrane into a 3-dimensional structure. And in the next 2 chapters, I'll show you that. So in this, I have only one kind of rod. If I add another rod into how their morphology changes, and in chapter 4, I will show you that by using all the information that I have learned from these first 3 chapters, how I use them, assimilate them, and then to assemble a colloidal graph similar to Pickering emulsion-like in appearance. Right. So let's start with chapter 1. So title of the chapter is Curvature Instability of Chiral Colloidal Membranes on Crystallization. Now let's look at some of the curvature instability that we see in and around us. Many of you must have seen this plant leaf, edge of this plant leaf. Some of them are not straight. They're always wavy like pattern, right? The next is a fried potato chips. They are buckled. So if you take a raw potato slice, it will be sort of flat. When you fry it, it becomes curved, right? So similarly, you can have, if a healthy RBC is a biconcave shape, if you have disease like sickle cell anemia, it transforms into a shape of a sickle. So that's how the name also comes from there. You can have heterogeneously solid gel, it goes like this. Now all these things can be schematically depicted in this. So if you consider a ruler of length L, thickness T, now if you compress axially, let's say some delta L, and it's in the pure compression, the elastic energy is proportional to the thickness of the rod. Okay. So, and if you have pure bending, then it's proportional to T to the power Q. Okay. Now if you decrease the thickness of the ruler, so the elastic energy in the pure bending or the pure buckling mode, so it will decrease way faster than this. So there will be a critical thickness somewhere, right? So this mode will be more favorable than, energetically more favorable than this. That's why it happens with thin plastic sheets. And our colloidal membrane is also having around a quasi-thin plastic sheet because L by T is around 100 or so. So what we do is that we assemble this virus with the colloidal membrane with these viruses and chlorine KO7, whose length is, as you can see, 1.2 micrometer, diameter 6.6 nanometer, and I use polyethylene glycol, which is a thermoresponsive polymer. So whatever is there, the crystalline order of the membrane, we find a peak corresponding to interseparation of the rod in this membrane. Now, looking at these two movies, of course, there are a lot of questions will arise that, first of all, why there is this kind of roughness? Right? What is the mechanism behind these two processes? Okay. And then what kind of, so also you can see that the membrane here is almost entire edge is focused, but here is not. So what is the structure, the continuum structure of this membrane? Okay, I'm going to answer some of the questions. And also, if I understand correctly everything why it is happening, is there any way to suppress this curvature instability or not? Okay. So next what we do is that we assemble this membrane at some intermediate polymer concentration. Now I use the temperature as my tool to go back and forth, meaning fluid to solid phase transition. So I will cool this membrane. You will see that there is nucleation somewhere starting from here. Yeah. Okay. And the domain that grows inside has a lot of wrinkle inside. Okay. Also, and when I sort of draw this growing front, I find the edge of this is faceted. Okay. And that probably indicating me whatever is growing inside has crystalline order. It's an indication. Now, if I allow it to proceed further, this movie, you will see that all the wrinkles will disappear suddenly, and then somehow the membrane will go out of focus here. Right? Okay. So since I use as a temperature, right, you will see local wrinkling and then global buckling. So because I use a temperature now, if I hit it back to room temperature or 30 degrees or whatever, then you will see that there is again melting. Okay, it will come back to original, and you can keep doing this process n number of times, it will give you the same result. So that's indicating that there is no permanent crosslink of rods there. So let it just, you will see that it will come back to, let it just melt it back, and you can keep doing that. So now the question comes, of course, why this kind of wrinkling is happening. So our collaborators from IIT Bombay started to think about this problem, and they considered, so they studied the orientational stability of this. So these rods are intrinsically chiral. Okay. So they studied the orientational stability of this chiral rod placed on a 2D hexagonal lattice with a circular torque-free boundary. Okay. So initial state was all rods are aligned along this z-axis. Right? So then, and they try to evolve the system using this Hamiltonian, which has got 3 terms in it. So the pneumatic term and the depletion term favors parallel alignment of the rods along the z-axis, whereas the chiral interaction, which is taking care of the chiral interaction of the rods, and generalized to have a preferred chirality of Q. So they found that in this spontaneously starts to form grain boundaries. So in their case, it is 2D simulation where these domain walls are pi walls. But in our case, what is happening? So the rods are falling on a lattice, and their interseparation is decreasing. So because of that, chiral interaction is increasing. So chiral energy is increasing. So now, so the rods can, to satisfy partially the chiral interaction, the rod can buckle up a little bit and then satisfy partial chiral interaction. So that's why you see this local wrinkling. Okay.
It's chiral interaction.
So yeah, so the rods.
Chirality emerges from some shape also, right?
Right.
So the picture you are showing, the rods, I do not see any chiral signature there. It can be
So it's
interaction or something.
So it's so because for all we can assume that it will be hard rod. Okay. But there is an intrinsic chirality associated with these rods. So it's not so clear why it is coming. So there are many arguments. So some of the thing that the virus is the piece of DNA coated with protein. So the DNA has got helical structure.
Right. So that can give rise to some handedness if it is DNA coated.
Right, exactly. Yeah. So here,
how is that taken into this Q? What it is doing?
So it's a preferred sort of. It's like wave vector, how much it will tilt. So it's like you see it at the
kind of.
And here it is normalized.
This one is lemma, this is just trying to align, and this one is trying to along the Z.
Yeah.
This term is trying to get rid of that.
Yeah, right. Yeah. So there are two terms which trying to
There's
favor
some
this.
parameter
Yeah,
just to destabilize this
Yeah, right, exactly.
alignment.
Yeah, right. So, yeah. So basically, in our case, they buckle out of plane locally to satisfy the current interaction. And so, yeah. So after knowing how local ridges are formed, now comes why there is global buckling. So here is a movie which I'll show you. This can you put up these slides? So here, so this is captured in fluorescence microscopy, where you can see individual rods. Those are fluorescent individual rods. So here again, so initially it will be fluid phase. Then I crystallize this membrane. Crystallization will start from somewhere here. You will see that. So the rods suddenly become immobile. They are falling on the plants. But what interestingly you will find that the rods at the edge are still moving. Okay, and in fact we find that they have a dynamic which will be of attachment and detachment to the solid core, meaning they will come back to the solid atom and then they again go out. So what I mean to say that here is that membrane edge doesn't crystallize. Okay, because a lot of chiral energy is required to sort of unturn everything and come to become a part of the plant. And you can see that all the green rods here are N30 which act as the emulsifier. So you think of in case of emulsifier. Now if I deviate, okay, so that's really high diffusion strength at 60 mg per nm. So now if I deviate slightly from this composition or the reaction concentration, you see that rods within the colloidal raft are homogeneously mixed. Okay. So yeah, another thing about these things are the kinetically metastable state because they are. You can see the polydispersity in the size of the domain as well as in the thickness of the ring of the green rod that you see here. Okay. So next question comes: how stable these structures are? So if I put them, many of them into the membrane, will they form a crystalline-like structure or not? So that's what I'm going to show you. So I'm going to show you the measurement of interaction potential between two of the colloidal raft. So there's a pair of ring-like colloidal raft. What we do is then we use optical blinking technique to hold these two rafts, which is generated from a single laser source using a optic deflector, and we hold them, bring them together, and allow them to diffuse away. And then from the equilibrium, the interseparation of this raft is given by this particular Boltzmann distribution, and is related to each interaction potential, right? And then from there we find that we do not find any significant difference for ring as well as the mixed colloidal raft. But what interestingly we find, if you take out the rods which form the inner core, the things become attractive. There is an attractive minima here, right? So still we don't know why this is happening, but still a lot of investigation is going on. And what interestingly find, so these are so we don't have the rod which have from the core of the colloidal raft. You will see that it will undergo a polymorphic phase transition. Okay. So it will initially circular. You will see that it will form a elongated horseshoe-like shape, a bound pair of horseshoe, which will engulf a circular domain of breakdown rock. Right. So yeah. And that brings to the conclusion of chapter 4, where I showed you that in an isotropic ternary mixture of rod-like particle at certain certain diffusion concentration, you can, or stoichiometry, you can assemble this colloidal raft similar to flickering emulsion like colloidal raft. And I have shown you the assembly condition and the choice of the rod. And we find that colloidal raft form this kind of configuration, they are weakly repulsive, and if you do not have this inner core, then they become repulsive. Now that brings to the summary of the talk, where in the first chapter I showed you that if you take a isotropic mixture of this rod-like particle and mix them with polymer, they assemble a colloidal membrane. And I showed you the existence of a novel curvature and stability 2D flat colloidal membrane because of the chiral nature of this virus, which shaped the membrane into three-dimensional structure through local wrinkling and global buckling. And then the second chapter, I add another rod into it, so a mixture of short, thick, and long, thin to say. And when I mix them with a depleted polymer, they self-assemble in the cyclic polygon-shaped colloidal membrane, and where the pinning junctions form cornerstones of the geometry, and we find that the pinning junctions are locations of compressed defective rods instead of being topological defect. Right. Then third one, I've shown you that if you take mixture of two oppositely chiral rods of having similar length but different rigidity, they separate to form an isotropic colloidal raft like this. And its morphology of this colloidal raft completely depends on the kinetics of the phase separation and concentration of the polymer. And the last one, I showed you that using all the information here, I tried to assemble a colloidal raft similar to Pickering emulsion like colloidal raft. Yeah. Thank you. Before I go into it.